Very warm welcome to this new edition of our Research Futures webinar. I am Leila Shukroon. I'm Professor of International Law and Director of the University of Portsmouth's Democratic Citizenship Team. A few months ago, we'd welcome Professor Bob Nichols to give a webinar on a similar topic, at least something similar to me, as I'm not exactly a specialist. But today we're welcoming our colleague Albert Izard from the University of Portsmouth. As you know, in the context of a webinar entitled Research Future, I'm very keen to welcome young scholars and give them the floor. So Albert is going to address the following issue: shedding light on a dark universe, a very vast question. What's Albert's profile? Albert is a research fellow in cosmology at the Institute of Cosmology and Gravitation of the University of Portsmouth. Prior to joining the university, he was a postdoctoral researcher in cosmology at different institutions, GPL in particular. He got his PhD in physics at the Institute of Space Sciences in the Universitat Autónoma de Barcelona in Spain. And he's already published a lot, developed a number of things, including new numerical cosmological simulation, something he's certainly going to explain to us. So without further ado, Albert, I give you the floor for your presentation. And as you all understood, we need to ask questions to Albert using the chat box. The floor is yours, Albert.
Thank you so much, Leila, for this nice introduction. Also, I want to thank Gia and Claudia for helping organizing this. And thanks everybody for coming here and wanting to listen to this talk. So it was really interesting to prepare this talk because I'm a cosmologist. In particular, as Leila was saying, I work developing cosmological simulations. But also these seminars have an emphasis on interdisciplinary research. So I did the exercise of finding the many examples that there are of applications of knowledge from cosmology, from astrophysics, that can be applied to many different problems in research in different fields. So okay, let's get started. So okay. I want to start showing so that everyone can have an idea of what is the universe. When we observe the universe, what's there? So we are more familiar with our planets and our sun, the solar system. These are the closest neighbors we have. But if we look further, there are more and more stars. All these stars are part of a galaxy, a medium big size galaxy, the Milky Way. But there are many and millions or billions of other galaxies in the universe. So in this diagram, we are in the center for artistic purposes, but the Copernican principle says that we are not in a privileged position in the universe. All the positions of the universe are equally interesting. If we put ourselves in the center for this representation, we see bigger and bigger objects as we move further from the center. And as we go further, there are many galaxies that they form a structure that I will explain much more in the coming slides. I want to emphasize this diagram is compressing different distances, different scales by a lot. So we're going to go through this. The scales in astrophysics. Okay, so imagine we're going to do an experiment with distances. Imagine that here on the left, that the Earth was as tiny as the very famous nowadays coronavirus. If the Earth was the size of the coronavirus, the sun would be at the distance of the thickness of a credit card. And then the next star, the nearest star to the solar system, it's called Proxima Centauri. It's in this image. This star would be at the distance, the size of the Spinnaker Tower. But then there are more stars in our galaxies, and if we wanted to represent the size of our entire galaxy, it would span from Portsmouth all the way to Turkey. And remember that we started that the Earth is of the size of the coronavirus. But of course, we can go even further than this. There are more galaxies, as I was saying. but I'm running out of distances. We need, again, to make the Milky Way, that before was the size of the distance to Turkey. Now, instead, I'm saying that the Milky Way is the size of a small car. Then, one of the most important neighbors in our galaxy environment is the Andromeda galaxy. So this galaxy, again, would be at the distance of the size of the Spinnaker Tower. And the farthest galaxy that we've been able to observe, it's a very distant galaxy. It's almost like this blob of light, would be at the distance from Portsmouth to Malta. So if we want to even visualize this even better, there is this animation that goes through. This is an animation, but it's based from real observations. So the shape, the colors of each galaxy comes from a real picture taken from a telescope and a camera attached to that telescope. And then from the telescope, we measure positions, we measure distances, and we are able to create this three-dimensional map of the positions of galaxies that looks like this. And in this representation, in this visualization, we can move through this three-dimensional map. So I want you to notice first how big this is, how many galaxies, millions and millions of galaxies in this animation there are, and then how galaxies like to live together. They because they feel gravitational forces. Galaxies are very massive, and they feel attracted to their neighbors through the force of gravity, and they form these clusters of galaxies, we call them, in which there may be dozens or sometimes even hundreds or even thousands of galaxies living together in a cluster of galaxies. So cosmology is the study of the universe at these scales, at these distances, trying to understand what's the universe made of, what's the properties of the universe, and this is the image that we need to have in mind when we are talking about cosmology. It's this distribution of galaxies at these distances, which tells us so much about the properties of the universe, what's made of, what's been the evolution of it, and with the statistical properties of it that tells us about its content. So as I was saying, I started from the Earth, solar system, stars, galaxies, and clusters of galaxies. Clusters of galaxies is the biggest object that exists in the universe. Bigger than this, I will show it. Well, I've been showing it in this visualization, but there aren't really bigger objects than clusters of galaxies. This one in particular is called the Bulet cluster because it's actually two clusters. One here, if it's a bit hard to tell, but you can notice that there are more galaxies. I hope you see my cursor, right? My pointer. So there are more galaxies in this location and also more galaxies in this location. These are two clusters of galaxies that they are actually very close to each other, and they are merging. I will explain this further in a couple of slides. But the main idea is this: galaxies are very massive. Therefore, gravity creates a strong force between galaxies, and galaxy neighbors start to get closer to each other and form these big associations that we call clusters of galaxies. And we can think of this process similar as if like drops of water that form in a glass. When there is condensation, first we see that small drops of water start forming, and then these merge to form bigger and bigger drops of water. And this is how galaxies form. We start with having small galaxies, then small galaxies collide with each other, they merge, they form bigger galaxies, and they also interact with the environment, and they form these clusters of galaxies, starting from small galaxies to bigger galaxies as time goes on. So I've been saying that gravity is the important force, and has driven the evolution of the universe. It's the most important force in the universe at these big distances. So the question is, why does the universe look like this? That there are these galaxies and clusters of galaxies. How the universe started and how now it looks like it does nowadays. So well, I here have here on the right in this slide a comparison. The universe is expanding, and because of this, well, earlier in the early stages of the universe was much more compressed, more dense, and more hot. So imagine like this situation in front of a live concert outdoors, in which there is a lot of people, very crowded. In English, I think there is an expression for this. It's a mosh pit, right? Everybody's dancing, very happy, moving a lot. So it's impossible or almost impossible to find a hole, an empty region here. Why? Because people are dancing, are excited, they are moving. So as soon as a small hole forms, someone will come very quickly and take that hole. So the hole will disappear very, very quickly. This is how the universe was in the early stages. It was because it was very hot, everything was moving around. We didn't have stars, we didn't have galaxies. Matter was floating in space. And it was so hot that the same as this mosh pit was the situation in the early stages of the universe. But the universe expanded. This expansion cools down, the temperature goes down, it cools down, and then things move slower and gravity starts to dominate. And when gravity starts to dominate, as you can see in this park on the right, people start to cluster. There are gaps between different groups. There are empty regions. And this in the universe would be because of gravity. Galaxies attract each other and they get closer, but then they leave other gaps, other empty region in space. So on the left now, this is actually an animation coming from one of my simulations, in which you can see as time evolves, this simulation shows how the matter content of the universe evolves in such a way that gets more cluster and cluster and leaves voids in the middle and regions of empty of matter. So the final state, this would be how the universe looks nowadays, with very dense regions and empty regions in between. And we call this the cosmic web. So I'm going to be talking quite a lot about this. The cosmic web is this filamentary structure. There are some knots, very high density regions, and filaments connecting these dots. So then I'm going to tell you that galaxies form in these very dense regions. So in this image where you see a very bright place, white color, this is where galaxies live. And the regions that are black are mostly empty. So we don't find galaxies in these areas. So you have to think of this filamentary structure is like a map of what I showed before in this animation. If you remember, this would be, if we zoom out even a little bit more than this animation, the final result is a map that looks like this. Okay, so let's recap a little bit what I explained so far. What are the properties of the universe? I've been saying that the universe contains stars, planets, galaxies, and up to clusters of galaxies, and distributed in this shape of cosmic web that I talked about. This is because gravity is the most important force and creates these shapes, and because of also the component of this expansion that created this, that led to this evolution of the universe in this way. As the universe cools down, structures started forming in the way that I've been describing. So okay, so far so good. I hope this is a more or less clear picture that we are able to understand quite well. But well, I'm gonna put some challenges here. Things are not so easy, unfortunately, or maybe fortunately, so that then there is people like me who are interested in this can have a job and work trying to understand what's going on. So there are more complicated things. What I said before about the content of the universe, stars, galaxies, clusters of galaxies, these are atoms. These are made of atoms, the form of matter that we are familiar with. But there is more than this. There is, we are quite convinced, we are still not fully yet, but we are quite convinced that there is something else that has a different, it's different than atoms. It's a different type of particle in physics. We call this dark matter. And also there is something even more like bizarre, that is a dark energy. So if we made a pie chart, the cosmic pie, we call it, of the the matter content in the universe, here in the bottom right, we see that atomic matter, galaxies, stars, what we are more familiar with, is just 5% of the content of the universe. We believe, we have evidences that dark matter is 25%, so 5 times more dark matter than atomic matter. And this creates an extra attractive force. There is more matter, therefore more gravity, more attractive forces. But on the other side, dark energy, this almost around 70% of the content of the universe, has the opposite effect. It creates a repulsive force, and because of this repulsive force, the universe that is expanding, it's doing it faster and faster. So the universe tomorrow will be expanding at a faster rate than it was doing yesterday. And this is what we call an accelerated expansion because of this repulsive force from dark energy. So okay, now I put the challenges. Let's try to explain this a little bit more. What's dark matter and what's dark energy? Let's start with dark matter and why we think that there is more matter out there. So if you recall, this is the Bulet cluster. And we believe that the Bulet cluster is an example that shows why there is more matter than what we can account. If we take a telescope, we take a picture of this cluster, we can observe the light coming from the galaxies, the stars that are inside these galaxies are emitting light, and this is what we see in this picture as the shapes of many maybe hundreds of galaxies that we see in this picture, right? And because we can measure how much light there is, we also can infer how many stars there are in this picture, how many galaxies and stars, and how much matter in the form of atoms. But then we believe that there is dark matter around it, and I'm gonna show you the next slide. The Bulet cluster, in fact, this is how it looks like nowadays. But in the last millions of years, it evolved as it is shown in this representation. These are actually the two clusters. The Bulet cluster is formed by two clusters of galaxies. And here I'm showing how the components of these clusters evolve. Clusters contain dark matter and atoms. And I'm going to show how dark matter that is in blue in this animation, and atoms that is in red in this animation, how they evolved until nowadays. So I'm gonna hit play, and the two clusters collided. And because atoms, the matter we are familiar with, atoms in red, have these frictional forces, like if you rub your hands, or if you take a piece of paper in the air is creating friction in the paper, right? This is why a paper can stay in your hand if you move the paper with your hand. This friction slows down things, or like if you're driving a car, the wind is trying to slow down your car, right? So atoms, normal matter has this friction component. And when the two clusters collided, we can see that the atoms in red are in these positions. They slow down. I'm going to play again this animation. As the two clusters collide, atoms slow down, but dark matter is kind of invisible. It doesn't emit light. And more importantly, it doesn't have friction. It only interacts through gravity, so it doesn't have friction, and it's like transparent. It collides and it keeps going. So after the collision, atoms slow down and they are in this blob and this blob, but instead dark matter is farther away here and here, and we know this. So in this animation, in this visualization that I'm showing, you can also see the blue color here and the blue color here. We are able to tell that there is a lot of matter in these blue regions because of a technique that I'm going to explain, a technique that is called gravitational lensing. But the important thing is that we know that there is a lot of matter in this blue region, more matter than what we can explain. Therefore, we believe that there is extra matter in the form of dark matter in these blue blobs. So, okay, and now I want to explain how this technique of weak lensing, I'm going to say again, this technique of gravitational lensing, this is a very cool idea that is based on the theory of gravity from Einstein around 100 years ago. General relativity, Einstein discovered or created the model of general relativity, which is a more evolved model of how gravity, the properties of gravity, the theory of gravity. And in general relativity, what it predicts is that when there is a huge amount of matter, this matter is around to bend the light that is traveling around it. So imagine that we are in the Earth here in the left. We are looking at galaxies that are very far. In the middle between the background galaxies and us, imagine that there is another very, very massive galaxy. The gravity of this galaxy is going to bend the light that is coming from the background, and we are going to see that the images of background galaxies are distorted in a way that is shown in the right in this slide. So imagine, okay, I need to explain a little bit more. This picture on the right is an experiment. Imagine that we are able to with our hand to move the position of this galaxy in the middle, and let's do the experiment of how the galaxies in the background would look like as we move this object in the middle. We would see something like this, that the background is distorted in this kind of shapes. So if we take a telescope, we take a picture of many galaxies, we can see patterns like this. We can see that galaxies have shapes that are distorted, and how strong is this distortion is telling us how massive is this object in the middle. So therefore, we have a method to weigh the mass of this object. So we can put this object in the scale and tell how much mass there is. And using this technique is how this map was created, and we are pretty confident that we need more mass here than we can account just counting how many galaxies there are in these locations. So this is an evidence for the need of dark matter in our experiments. There is more. Already in the 70s, Vera Rubin was an astronomer, an astrophysicist that was studying how galaxies rotate. So I'm gonna go to the next slide, to this animation. when you have a system that is rotating, and I'm gonna warn you that this video is a bit goes a bit crazy towards the end, so be prepared for that. But I think you can already suspect what's gonna happen. This is not a good idea when a playground that should be for kids instead boy teenagers go there and do their experiments. So we're gonna take advantage of this video and see what's the experiment, what happens in the experiment. If you a system that is rotating very fast, as the faster it rotates, you need a very strong pull so that things keep rotating in the position that they are. If this pull is not strong enough, what happens is what you're gonna see. So, well, this is what happened. So going back to astrophysics, Vera Rubin in the 70s saw that stars in this type of galaxies, spiral galaxies, were rotating very fast, faster than that was expected. And to rotate so far, so fast, you need more mass than you thought of. In the center of the galaxy or around the galaxy, you need dark matter, more mass in the form of dark matter that is pulling stars, so that stars don't do the same like in the video that they get ejected, so that they keep circling around the galaxy and the galaxy doesn't get disrupted by such a strong velocities. So this is another evidence that we need more matter than we were able to observe. So another recap here, we have different methods of putting the universe in the scale and looking at the number that in kilograms, how many kilograms different objects in the universe weigh. So I talk about the rotation of galaxies, I talk about gravitational lenses, and there is more. We can look at the large-scale structure of the universe, the motions inside galaxy clusters, other observations of different radiation that all are evidences that there is more matter than what we can account by just looking at stars and galaxies. So this dark matter, what's dark matter then? Well, we don't really know yet. We think it has to be a type of particle. So there are in particles in physics, we have electrons, neutrons, protons, they form atoms. This is what we are familiar with, right? So, well, we think that maybe there is something we are still missing. There is a different type of particle, something different than electrons and protons and all this, that has the properties that I was describing. So these properties is that this dark matter particle doesn't feel friction, so it only interacts through gravity. And then this would be a bit longer to explain why, but this type of matter doesn't emit light. It can form objects like stars or galaxies. To form a star or to form a galaxy, you need frictional forces, you need processes that emit light, and dark matter doesn't do that. So then again, here I'm showing the cosmic web, and this is a representation of where dark matter is in the cosmic web. And there are these nodes and these filaments where we find galaxies and dark matter together. So where there is a galaxy, there is like a sphere, a kind of sphere of dark matter around the galaxy. And also when there are clusters of galaxies, many galaxies in very close together, all this is also embedded inside like a huge and very massive dark matter halo, we call it. Okay, but I said dark matter and dark energy a few slides ago. Dark energy instead has this different behavior that is repulsive. So it was observed in the 90s, and this was awarded by a Nobel Prize, that the universe is expanding faster and faster, as I also said before. And to explain this, we need a repulsive force. Mass or like if we here in the Earth, let's do the experiment that we are in a very tall building and we drop an object from the top of the building. The object will start falling faster and faster as time goes on. This is the behavior of matter, both atoms and dark matter. Dark matter behaves in this way as well. But dark energy instead has this opposite effect, that it's repulsive. So if we drop a ball and if we were, this is not how it is, but if we were really able to be in a place with dark energy, instead the ball would go up instead of down somehow to have a visual image. And this explains why galaxies are separating from each other faster and faster because of dark energy. The observations point in this direction, that we need dark matter and dark energy to explain observations. And in the current model, this explains many things. We can account for many observations in cosmology. But the problem is, okay, so what's that? Well, I don't have an answer. We don't know yet. We think that dark matter is a new type of particle that we have to discover. And similarly, with dark energy, there are different possible explanations. One of them, also interesting, is that maybe we don't understand the laws of gravity. Maybe the laws of gravity are a bit different than what we think. I said before that general relativity is actually the most up-to-date theories, is the theory that explains many things, but maybe we need to tweak a little bit general relativity so that it creates this kind of effect that things seems to be expanding faster and faster. This could be a possible explanation for the accelerated expansion of the universe. So here we are trying to fix this problem, or try to understand it. So we have a consensus cosmological model nowadays that is based on some of these elements that I'm listing here. We think that the universe, as we understand it nowadays, started after a big bang or a big expansion. That the universe is made of different matter components, atoms, dark matter, dark energy. We think that that general relativity seems to be a correct law of gravity, although I was saying that maybe we need to tweak this a little bit. And these problems that we don't know what these mysterious dark components are. And also there are more complicated models that could also be consistent with the current observations. So we need to investigate this further. So here in my presentations, I like to frame it this way. We have nowadays three main ways in cosmology to understand things better, to get some knowledge. So the most important one, I would say, is observations. In science, we need to see what's there, and only models that are compatible with what we see with our observations should be the valid ones. But on the other side, there is this theory. So we have to propose models, laws of gravity, or possible theories that can model the fundamental laws of the universe. And on the other side, in astrophysics, we have this problem, right? Where do we do the experiments? Can we set up a lab and put a little bit of some stars, some galaxies, some dark matter, and see what happens? Well, it would be quite difficult, right? So instead, we do simulations. We use computers in which in the computer we tell the computer some laws of physics, and we do some experiments inside the computer to see what would happen if these were the correct laws of physics. And this is really, really important nowadays. Also, I'm going to connect this in the next slides, but current observations, current experiments produce huge amounts of data, and analyzing these data sets also it's a very hard task. And before doing that, it's very good to do simulations in a control environment. A simulation is something that we create ourselves in the computers, and we can do some experiments of how we are going to analyze so much data in the future. So I've been talking about simulations. What's a simulation, right? Let's explain this a bit further. Also, this is my main area of research. So here on the right is a visualization of one of my simulations, in which we see how this cosmic web in the background, and then we can, once we create these huge data sets from simulations, we can try to do an experiment of imagining that we live in this simulation. We are looking at the sky, at the universe, what are the maps, the things that we would see, how it would look like, and create synthetic observations before we go to the telescope. So, okay, a simulation, it's this recreation inside the computer of a synthetic universe. We we code the law of gravity and the properties of matter in the computer. We hit play, and then we see how this evolves in time, and we reproduce, we form this cosmic web in the simulation. So I already said that this can be very useful to first to see what would happen if this was the correct model. How would the universe look like? This is very useful to do model predictions, and also to be prepared to analyze the future observations. We do first synthetic observations inside the simulations. The challenge is that simulations are hard. They require big computers with many processors, infrastructures, and like lots of things. And sometimes this is actually a problem, that we need bigger and bigger computers to run these simulations. Well, we do the best we can with the resources, and always like push to have the bigger, as big machines as possible. So then, the other leg of this triangle of knowledge: observations, theories, and simulations. So going back to observations, one of the areas that I'm also very interested in is galaxy surveys. This is a type of observations in which we go to an area of the sky, and we take a very detailed picture of that area, and we see things like this one in the background. We see millions of galaxies, and also it's very interesting that the size of this image is compared to the size of the moon here in the bottom left. It's only this tiny area. So the sky is so big, and we can take so many pictures like this. So we need very efficient telescopes and cameras that can take hundreds and hundreds or thousands of pictures and create maps of the positions of the galaxies in the sky, so that then we can create this animation that I showed in the third slide or so, and understand that this map of the structure in the universe. So some very interesting coming projects. One is Euclid, is a mostly European project. It's a telescope that will launch in a couple of years, a telescope that will go to space and will take pictures of millions and millions of galaxies. Another very interesting one is the Rubin Observatory is gonna start observing in about 1 year from now. It's gonna be a survey of the sky, and look at how big is this is the camera for this survey that this woman is holding, and how big it is. Imagine to compare this to the size of the camera in your smartphone, or the size of the camera, the chip, the sensor inside a professional camera that a professional photographer uses for pictures in the earth. This is how big this camera, that has 3,000 megapixels, and it's so big that in one shot, this is like, of course, it's like photoshopped here inside the image. It's the size of the moon. This sensor is so big that in one shot you can get an area that, compared to the size of the moon, it's so big. And compared to the previous generation of surveys, this image in background, this is a huge step. So this is how we create these surveys to understand um, to understand the cosmic web. I'm gonna skip this slide because maybe I'm gonna run out of time. So okay, this is, I think, an overview of our understanding of the current consensus model in cosmology and the current experiments that we're trying to do to push this further to understand the missing pieces that we have. So finally, I promised that I would talk about other applications or applications of this knowledge to more down-to-earth applications. So let's go to it. So now I'm going to ask you to look at this image in the top. Don't read the text, please, and try to think, what's that image? Is this image maybe the positions of stars in the sky, or maybe the positions of galaxies, or something about dark matter, or the cosmic web? Well, actually, it's not. So I'm going to tell you, this is an image of droplets from a cough. So this is related to COVID. So this is an image. Imagine that we know that surfaces, COVID, the viruses may stay active for days or many days in hard surfaces. So when someone is coughing, we create all these droplets. And there is a team in my institute, in the Institute of Cosmology and Gravitation, that is taking images like this, using the software that we use in astronomy to identify objects inside the image, to identify these droplets, and then characterize them. How many droplets there are? What's their size? And how many of the big ones there are? How many of the small ones there are? And from that, we can understand better how important is the transmission of COVID from droplets of water when we cough. So yeah, I think these are very and like very in the current circumstances, this is very, very interesting, right? Other examples. So there is a colleague in my institute, a research fellow, Chris, who is a specialist in supernova explosions. So this means that suddenly in a galaxy looks very quiet, peaceful, and maybe suddenly one day a new star appears. It's actually not a new star, it's a star that was already there, but that exploded and suddenly it got as bright as the entire galaxy. So you see here an example of this. So he's a specialist on this type of things. So these are things that change in the sky. You look at a galaxy one day, there is nothing. You look at the next day and there is a new star there, or you see this new star there. So you need to analyze the evolution in time of your images to detect these objects. So he's using his knowledge to develop applications like mole gazer. This is people who have many moles on the skin, and some of them may become may develop cancer. So he developed an application to study the evolution of the moles and to identify the ones that are likely to become to develop cancer before this happens, so that you can intervene. He's also been doing work with the King's College Hospital in cardiology, using statistical methods to predict the presence of coronary problems, also problems related to hypertension, also using algorithms that we use in astronomy to decide if you need to use some drugs or not to treat hypertension. Other examples. So this is a colleague from Barcelona who works is transition this year. He's transitioning from cosmology to health to epidemiology. He's going to work in the Barcelona Institute for Global Health. So in cosmology, he's a specialist in analyzing the cosmic web. So this this filamentary structure, we need statistical tools to quantify, to put numbers into this. We are scientists that we need to quantify things, so we need statistical tools to quantify this distribution of matter. So he's gonna use this knowledge to model how malaria spreads, to identify hotspots and the transmission, all the epidemiology of malaria. So there are many similarities here, right? Also, as well. Another project. So this is from Samuel Farrens. He works in this lab in Paris, the Cosmostat. He is a cosmologist that works trying to measure the shapes of galaxies, to show how difficult this is to measure the shape of galaxies. This would be how a galaxy would look like in a perfect experiment, but this is not the case. We have the atmosphere, we have instrumental problems, we have pixelization, we have noise. So we observe the image on the right, and we're trying to model something that originally was like in the left. So this is a very hard problem. So he's become an expert on image processing techniques, and he's using this to develop image reconstruction techniques and an analysis software that can be applied in medical applications, in scans like MRI, microscopy, electron tomography, and so on and so forth. Okay, I think I have time. I think this is the last slide. Finally, I wanted to, yes. So this is a bit of an extra slide, but I thought it was good timing before finishing. That when was that? 3 weeks ago, the latest Nobel Prizes were announced in physics, and this year we were lucky that this was awarded to research in astrophysics. In particular, I don't have time to explain all the science behind this, but there are basically two things that were awarded. Roger Penrose was awarded for a theoretical work with the maths related to the math that you need to predict the formation of black holes. And on the other side, Reinar Genzel and Andrea Ghez were awarded for discovering a supermassive black hole that is living in the center of our own galaxy, the Milky Way. And also, it's worth noticing that Andrea is the first woman to be awarded a Nobel Prize, a first astrophysicist to be female astrophysicist to be awarded a Nobel Prize. So this is something new and worth to mention. So that's all from my side, and I'll take questions if there are. Thank you.
Thank you so much, Albert. That was really very interesting, fascinating, and thank you for concluding with a number of quite practical applications, really, because I think it makes the understanding of what you're doing easier and gives a great illustration. I know that some questions are coming up in the chat box, but I'm going to ask the first question because you kindly invited me to give a lecture recently to your colleagues in your institute, and we discussed the concept of positivism amongst a few other things. So I was wondering, you see, because your specialism is really simulation, if I understand well, and as you explained, the use of computers to sort of reproduce or maybe therefore see what happens in the universe. So tell me, in terms of somehow practical, I think you've explained, but somehow in terms of ethical rather issues, what do you face, if any, ethical issues when engaging in this work of simulation?
Well, I don't have like something specific to simulations or to my very specific field, but maybe I would say that research is very competitive. Resources are hard to get, and there's always a competition, and I guess there is always this component of how to assess who deserves to get a job or to get money, to get resources, to which how do you say which applications are approved or not. So I guess this is where ethics and implicit biases and all these problems that we all have to a certain degree are important. I'm not sure if I understand the question, or if there is something specific to.
Oh, you did very much understand the question, but what I had in mind as well was this idea, but maybe, you know, I'm completely mistaken coming from a very different field, but I had this idea in mind of, you know, you working on the basis of a number of laws and assumptions which might not be necessarily shared by the entire scientific community in your field, or am I completely mistaken and everybody agrees and it's a very, to use this example again, positivistic vision, which is the same for everyone?
Well, so yeah, in science there are different currents, or like different, or also it's very competitive. Sometimes different teams are trying to publish results first, so there is competition here as well. And also another component also is like for instance in astronomy we need to build sometimes very big infrastructures like telescopes in the top of mountains in remote areas. And there has been a controversy, for instance, in an example is in Hawaii, where the native people there how is that the native people feel like a kind of in their culture mountains are like a religious place, and astronomers are going there to build the big telescopes at at the top. So how this is explained to these communities and these problems are solved, it's currently a problem, and there is not good solution, and there are problems about that. There have been protests, so this goes in this direction, yeah.
Fantastic. Thank you so much for this response, Albert, and sorry for the sort of challenging question. We have a question from Sylvia. How do you confirm the accuracy of a simulation if it is modeling a part of the universe that is so far that is unobservable? Have you come across researchers who did simulation that contradict your simulation? How do you reconcile that? So somehow it relates to the previous question. You want me to read it again? How do you confirm the accuracy of a simulation if it's modeling a part of the universe that is so far that it's unobservable? Have you come across researchers who did simulation that contradict your own simulation? How do you reconcile that?
Yeah, that's a very good question. It's first I would say that a simulation is a controlled environment. So you know what ingredients you are putting in the simulation. So up to a certain degree, you know what you can expect out of it. So it's a choice of the simulator of I want to do the simulation this way or this other way. I want to do it more accurate or less accurate or bigger or faster. So all these are choices up to the simulator. And then it's true that you have to validate the results of your simulation. You have to show to the community, if you want people to believe you want to show that your results are compatible or comparable to previous studies. And if there is something that doesn't match or that it's different, you have to show why this is the case. So yeah, I don't think I would say that I've experienced like other teams having simulations that contradict mine, but it's more like a complementary game in which different teams uh, develop slightly different types of simulations that focus on different aspects, and we all learn from these different this complementarity.
Excellent. Thank you so much, Albert. We have another question from Michael. Do you personally believe in dark matter and dark energy? And do you think it will be possible to detect them more locally than the Bulet galaxy cluster?
Well, so this is why we are doing research, big teams of people doing research. I personally think I'm maybe a bit conservative, but yeah, dark matter and dark energy seem a very good explanation of what we observe. There are more exotic theories or suggestions to explain observations, but dark matter and dark energy are seem to work very well, and it's perfectly possible that there is a type of matter, a type of particle, something that we haven't detected it yet, and this is not a big problem as far as one day we detect it. Like if it's there, if we think that this is dark matter, one day we have to detect it. So there is people working on these experiments, trying to detect locally in the Earth, trying to detect the dark matter that is floating around the Earth. There are many experiments trying to do this, and they are getting bigger and bigger to try to be more sensitive and more sensitive, to try to find if this particle is smaller or explore all the possible options for a dark matter candidate. And well, the plan is that sooner or later it may take five more years or maybe 50 more years. We don't know, but one day we hope that that if dark matter is explained by a new type of particle, we will detect it at some point.
Excellent. Thank you so much again, Albert. We have a question from Curtis. Following on from the last question, is it a matter of belief? That said, does it seem counterintuitive that we seem to know about 5% of the universe, but not the other 95% comprising dark matter and energy? Shouldn't it be the other way around? Or is it that we are at the very early days of research here?
Oh yeah, okay. So that's an interesting point of view. I wouldn't say we are in the early days. We've done already quite a lot of progress, but clearly we are not that close to the end yet. So I would say, yeah, in science, so sometimes maybe in this presentation I used the word belief or this type of things, but more correctly I should say we have evidences that something is missing. So when we see, so we observe a cluster of galaxies, let's say, then we use the models that we think they are right to explain what we observe. And then we see that something is missing, something doesn't match. So we have some options. Either there is a new type of matter that we are not able to detect that would explain this discrepancy, or the models that we use to analyze these observations are wrong. So what we know for sure is that there are some things that are not matching. We have evidences of this, and this is what I tried to explain when I was explaining dark matter, that the observations from gravitational lensing, the observations of rotational curves of galaxies, there is something that doesn't match there. And the more natural explanation is to say that there is dark matter. But yeah, we still haven't seen it, so it's a bit obscure, mysterious, however you want to call it. But it's not just a belief, is that we have evidences that some things are not matching. Therefore, we need to come across with different ideas, new concepts, new models, or new types of matter, something we need to incorporate into our models.
That's great. Thank you so much, Albert. I'm afraid it's going to be the last question because we're running out of time, but you concluded on an interesting note, the idea of not even, maybe if not progress, at least evolution of science, and always, getting more knowledge. And I very much like the triangle of knowledge metaphor that you've used. I can see, let me see that. There's a last maybe, it's an additional comment from Curtis, so let me read that to you. Is it time for another Einstein who can look at things from a completely different angle in the same way that the novel, that he moves things on from Newton? So maybe you're going to be the new Einstein, Albert.
Well, that would be great. Thank you. Well, sometimes people say this, we need like a new Einstein. Yeah, this is like a good way to say it. Like a big mind, like to revolutionize the field or something. Maybe it's true, or maybe this is not realistic nowadays. Now science has evolved so much. We have so much knowledge, so many tools, statistics, simulations, data theory. It's so big, and things are done in big collaborations. So these collaborations are observations that I briefly mentioned in the talk. There are hundreds, if not thousands, of astronomers working in these projects, and all of them are very, very, very good scientists. Maybe they are not geniuses like comparable to Einstein, but like some of them maybe they are, and all of them are very good scientists. So this is how science works nowadays, with big collaborations, a lot of organization, common projects, different countries building infrastructure together. This is how science is progressing faster nowadays.
Right, and that's also a very interesting observation and great concluding note, because this is very interdisciplinary from what I understand, very collaborative, very global as well. So, and maybe we're going to make more advances, progresses, evolution in working that way rather than relying on one genius, you know. And this is something we can say about many disciplines actually in research and science. Again, thank you so much, Albert. That was really very interesting. Thank you for making this accessible to a larger audience. I think we all were following very well and understanding everything you said. You had great comments which are a proof of that. Everybody, you know that the lectures, the webinars are always recorded and are available on the website of the University of Portsmouth under the banner Research Futures. Gloria is kindly sending you the links in the chat box. You can always find all our webinars on the website of the university. We've had more than 25, and obviously we're going to have one more next week on a completely different topic. I'll be welcoming a colleague from India to talk about women dignity at work, women engage in very different professions in India and Nepal. So join me next week at 2 p.m. And as you understood, every Wednesday, 2 p.m., we'll have our Research Futures webinar. I'd like to thank the team, Gloria in particular, as well as Olga, Her, and Claudia for their support. And thank you very much for being such a great audience and asking that many nice questions. I'll see you very soon next Wednesday, and thanks a lot again, Albert.
Thank you. Bye.
Bye, everyone. Have a great afternoon.